All right, I really hate microphones. Let's do it anyway. As I'm sure you're aware, if you're a mechanical engineer, I don't need to explain to you why this equation is important. If you're a mathematician, I don't need to explain to you why this is important. If you're a scientist, I probably don't need to explain to you why this equation is important. But I'm going to use mechanical engineering perspective. Heat transfer is very important for almost every mechanical engineer. So this kind of problem is an excellent problem to solve. There's a good reason for it. This 2D problem does have an analytical solution. So we are able to see how good our numerical solutions are. If you want to know what that analytical solution is, come and see me. I'll give you my MATLAB code, and I'll give you the proof. I actually teach it as part of the 工程数学 engineering mathematics course. So I can give you that information if you like. So this is an excellent test because we know the answer. We have a Fourier series solution to this problem, and we know what the answer looks like. Secondly, this equation is almost a Navier-Stokes equation for gas flow. And in fact, it's almost a lot of equations that we use in science and engineering. If I want to transform this to the Navier-Stokes equations, I need to add 2 more terms to this equation and I'm done. So it's an excellent code to have because when it comes time for me to add transport terms, add vection terms, we just need to add 2 more parts and then this code can do everything. And so that's very, very useful for us. Secondly, the reason I want you to do this is because when it comes time to solve this in parallel computing we use something called loop sharing. When we solve this problem, we do 2 things. One, we go over space and calculate who our left neighbor is, who our right neighbor is. 我们上面是谁，下面是谁，左边是谁，右边是谁。我们用它们算一个新的 temperature here. And we calculate the new temperatures at one spot. And then when everyone has a new temperature, we go to the next time. So what does this mean? It means that we have 2 loops. One of these loops, we can share the work. The space loop. In the space loop, it doesn't matter if you calculate this person first and calculate his left and right, or this person over here, 再算他的左边右边是谁. But, 重点是, you need to calculate everyone's new temperature before you can calculate the new temperature. 一定要算新的 t, 就会有办法算那个更新的 t. 所以我们会有2个 loops. We have 2 loops, one for time, one for space. In parallel computing, we have concepts in loop sharing. That means we can take loops and share them across different cores, but we cannot share time. We can't share time. We can only share space parallelization. We can only parallelize space. So that means when we write our parallel code, we are only going to parallelize the space loop. We cannot parallelize time. Because you can't use 2 CPU cores and say, second CPU core will calculate this time, and the first CPU will calculate this time. These are different times. 后面的时间还是要前面的时间。如果没有它的结果的话，就没办法算。So we need the old results to calculate the new results. So time is a serial computation. Space is parallel. We can make space parallel, but time must not be. Okay, let's get going. Today's class. So I hope you enjoyed the warm-up. It works now. What happened? Oh, that's loud. All right, today. Can everyone hear me? All right, let's get going. So today's class, week 4 of GPU computing. Today is a magical day. I hope you guys brought some kind of cake, chocolate, or coffee to celebrate. Today is a day you're actually going to perform a calculation on the GPU device. So last week we only allocated memory on the GPU, so we got ready to perform a computation, but we didn't actually do any calculation. Today we're going to perform a calculation. There are 2 calculations we can perform on the GPU. One is serial, one is parallel. Serial means we're going to use one process on the GPU. Parallel means we're going to use many processes. If you think I'm going to let you use parallel process today, you must be crazy. I'm going to make sure you practice serial first, so that's what we're going to do. Serial calculations are a way of describing basically what you're programming now. Everyone's code today, 每一个人写的那个 code, all uses one core when it's running on the computer. So this 现在的 technology 没办法拿你的 code 让它变成平行的。There's no way that we can take your code and automatically find a way to share it across your cores. So the C code that you guys are writing now is going to be created into a single process, which is what we call a thread. That thread will be allocated to one of the cores inside these machines. And while that process is running, the other cores are going to be idle, which is a waste. And so the mission is to teach you how to parallelize that, but there's no automatic way to do this. So I'm afraid that we're going to have to find a way to teach you. But today's class is about moving the same calculation onto the GPU device. And the GPU device is designed to be in parallel. So it's actually quite a tricky thing to do. 所以重点是我说 serial 的时候，你应该知道我的意思就是 one thread, one process. We're not running in parallel. We're going to try to solve the problem on one core. One thread is just a process. GPU is designed for massive scale parallel. 如果你有办法打开那个 GPU 看着里面 you'll break the GPU. Congratulations. Don't do this. I want you to imagine what's inside. There are, on the average, about 2,000 to 3,000 cores inside the GPU device. So when we normally produce work for the GPU to perform, we assume that we're going to use all of those threads. 今天是不一样的. We're going to ask it to do one thing. So that means most of the cores on this GPU today are going to be empty, idle. 它们是空的，因为我们就会请一个 core 在 GPU 上，然后我们跑这个计算。所以其实我们写的 code 应该不会改变很多了。So I can promise you, if you finished your code, if you have finished stealing my fantastic code that I wrote last week, make sure that you buy me some chocolate or something because I've done you a big favor. It doesn't take a lot of time to change that to run on GPU, I promise you. If you give me that serial code to make it run in serial on the GPU device, it will take me about 5 seconds work, maybe 10 seconds. I'm going to give you guys half an hour, so we're going to have plenty of time to do it. So let's do it. Today's class, serial computing on the GPU device. When we perform any calculation on the GPU, it's always going to follow a pattern like this. Firstly, we always allocate and never forget to free the memory on the host and on the device. So, 因为我们知道我们要跑计算在 GPU 上, we know we're going to perform the calculation on the GPU. We need memory on GPU, we need memory on CPU. If you don't allocate memory, you can't perform your calculation. We need to get the GPU ready by sending information to the device. We need to create instructions for the GPU to perform the computation and then find a way to tell it. Fortunately, this is quite easy because the creators of CUDA and most parallel computing paradigms actually make this quite easy for us. It's not as complicated as you might imagine. Today we're using a single thread, so this instruction is going to be quite simple. After this, we remove the information from the GPU, copy it back to the host, and then free, and then we're done. So, as a matter of fact, every week from now until when you graduate in this course, I'm going to say, what do we need to do to write a parallel program? This. It's basically always the same. Allocate memory. Perform the communications to get that working. Do the calculation. Communicate the answer back to the device. The host, sorry. So, you know how to do this. 现在每一个人应该知道我们怎么 allocate 那个 memory 在 GPU 上. Everyone should know this. If you don't, you guys have got the YouTube videos, just steal my stuff again. That's what it's for. I wrote it just for you guys to steal. These three we're not sure yet, so we're going to do that now. So we need to know how to communicate information, and we need to know how to create a function for execution on the device and then compute. So let's see. Talking to the GPU is like talking to your mother-in-law. It is not an easy thing to do. In fact, the GPU does not like to be spoken to. There are only several things we can do between the CPU and the GPU. Basically, transferring memory between the two is the only way to go. So we can issue instructions to the GPU, but those are in the form of kernels, which I'll show you shortly. But we can't use printf, we can't use fprintf. We must use a memory copy method to move the data to and from. So that's what we're going to do. Now, memory copy is actually a function in a C language called memcopy. The C language version is called memcopy. in CUDA, it's called CUDA memcopy, which is fantastic. It's almost like the C++ version. So C++ version of memcopy is basically exactly the same, but there are some small differences. So here is our CUDA function. This is what it looks like. I'm going to write it down. 现在知道每个人知道我们今天是用那个 port 912吧。If you don't know this, I don't know how you just logged into your computers because it would be impossible to do so. I'm going to write this down. Now, you guys should be familiar with this guy. This variable here, error, is a CUDA error type. 可能只有它的方式让你知道 copy data 的时候，如果有发生什么问题，那个问题应该是放在那个 error 里面。如果没有用它的话 how do you know if there was an error? There is no way of knowing. Geez, there is a way of knowing, but we're going to talk about that later. So CUDA memcopy, I'll write it down. CUDA memc is small. Now what's this first one? Now actually you should be able to figure out what these mean. This guy here is a parameter which tells us the direction of copy. So when we copy data to and from the GPU device, there are actually 4 different combinations of directions that data can go. In this case, we have what? CUDA mem copy host to device. So we're moving data from the host to the device here. 我们现在就是要把那个 data 从那个 CPU 到 GPU 那里。So this guy must be the destination. We can see that we've used the variable name DA. We know, I know, you know, we know, that is A on the device. That is why I picked the name DA. HA is the place where we're copying the data from, and it is on the host. Size is how much. So let's copy that down. And this guy, you can Google. This size is a size type, just like n times size or float, just like we do when we use malloc. Exactly the same thing, actually. Exactly the same variable, exactly the same result. So I've written that there for you too. 上面的是什么东西啊? This is the same line, actually, exactly the same code that we use when we want to check our error type when we use CUDA malloc. So you can see, actually, I cut and paste the same line all through my code. 我每次做什么 CUDA 工作，我以后就是会放这个 line. That way I can see, does CUDA have anything important to tell to me? Is there anything that I can take away from this error message? Most likely, because you guys are going to copy my code today, there should be no errors. Surprise me. I can't wait. I know it's going to happen, so I'm ready for it. Let's do it. So the 4 modes, I've written copy mode here, up here. This is not a variable. I want you to Google this. There are actually 4 different copy modes. The one I just showed you is CUDA memcopy host to device. That's copying data from the CPU to the GPU. Device to host. 应该知道那个是什么东西吧? We're moving data from the device to the host, from GPU to CPU. The magic is host to host. CUDA memcopy host to host is basically copying memory on the CPU to some other place in memory on the CPU. That's just memcopy. We don't use that. We won't need it. And device to device. If you have a variable on the GPU that you want to copy onto another device on the GPU, we use device to device. Device to device does not mean if our computer has 2 GPU cards, copy from one device to the other device. 这个很不一样。如果你要做这个工作，你一定要用 MPI. That's a different thing. I'm not going to cover that in this course. Device to device means one variable on the GPU to another GPU variable. We will use this. 所以你会用到的是 this one, this one, and this one. Don't worry about host to host. These are our pointers. float HA is our array on the host, DA is our array on the device. After you finish using malloc and CUDA-malloc, and we have our arrays and we know what they are, we can use CUDA-mem copy like this. If we want to copy to the device, destination, source, size, which is n times size of float if you're using floats, CUDA-mem copy host. So this is the same code I just wrote. The arrays do not have to be the same size, but the array you're copying must fit into the destination array. 如果你要 copy 的东西太大了，没办法放进去你的 destination. There will be a big problem, and we're going to talk about that soon. Oh, so if I give you a code like this, you should probably know what's coming. My advice would be, after you've finished having a working two-dimensional heat transfer code, save a copy of it. Don't lose it, because it's useful. Create a copy, then edit your old version, because you're going to have a different version now, and create a function like this in your CUDA file, because we're going to use this function here to copy something to the array, copy something to the GPU. So here we have a wrapping function sent to device. 这个 code, 我问你, do we put this code in our CPP file or in our CU file? Have a look. If I give this to my C, C++ or CCC compiler, GCC compiler, will it understand what it's talking about? It can't. It's got the function CUDA-mem copy in there. GCC, G++, it doesn't know what that is. It's an alien thing, right? If you try to use GCC to compile this, it's going to ask you what that function is and ask for an explanation. The easiest thing to do would be to put this in your CU file. So this function, we're going to use a CPU to call, but its definition will be in our CU file. So feel free to steal this. But I need to give it to you first. Getting information is done like this. Get from device. It's basically exactly the same code. Let's have a look at this. Here's send to device. We have a size and error type. Then we use CUDA-mem copy with DAHA. When we get from device, size, error, this time host. We're sending it to the host from the device. The size is the same, and we're using CUDA-mem copy device to host. Now, many things can go wrong here. It's like if you ask, your kid comes to you and says, I want to buy this lolly, and you say, take it back, and they come back with a better lolly, the message has been mixed. You're asking something to go one way and something's coming the other way. If you say, CUDA-mem copy device to host, but you put DB and HA here, what will happen? The GPU is not going to be happy. But if you're wondering what will happen to your code, please try today. So soon, this afternoon, when I give you a chance to write this code, I want you to do me a favor. Do it wrong. I want you to make this the destination on the device. That's the host. And then say you're copying from the device to host. So you're saying that you want to do it one way, but the two arguments at the front are mixed. I want to see what kind of error message CUDA tells you. I've got some good news and some bad news. It's mostly bad news. It's not going to give you a lot of information about what went wrong. But I'll let you guys make that mistake. One final warning. If your array on the host or on the device that you're copying into is too small, 如果你的 host 上有100万个 pieces, 但是你的 device 上只有1万个 array elements, 你要 copy 那个100万东西进去那个 GPU 的1万的东西，这个没办法吧？ It's impossible, it won't fit. You will get an error. This error we know is a segmentation fault. But this will be different to the segmentation fault you see on the CPU. When we use computers like this, and you get a segmentation fault, what does the computer tell you? Lots. It gives you a lot of error messages, and then at the end it will say segmentation fault. When you do this on the GPU device, what is it going to tell you? The GPU, remember, has no mouth. It doesn't tell you anything. So it's going to work. Your code will run. It's going to give you the wrong answer because you can't copy the data, and your code will crash. But no errors. GPU will not say a thing. So, there are many, I like this one. This is 3 examples on how you can create errors. If you have not allocated memory on the device, 如果你还没有用 CUDA-malloc, but you try to use CUDA-memcopy to copy information across, there's going to be an error. But it won't tell you. If you try to use the incorrect mode, there will be an error. You'll be lucky if it tells you. There are about 50 different errors you can make communicating data between the host and the device. I personally can't wait until I watch you guys try to do it. I'm going to see every kind of error that is possible, and that is perfect because that is how you become an expert, by making mistakes. Please do not set my GPU on fire. How will we know if a transfer to the GPU device is successful? This is easy. It's just like having a girlfriend and exchanging money. You give your girlfriend money, and then you tell her to give it back. After you get it back, you count it. If it is the same, then the exchange was successful. In GPU, we do the same thing. When we copy information to the device and copy it back, we can use this dual copy system to know if it has worked or not. We can copy information to the device, pull it back and place it in a different area in host memory, and then check to make sure if it's the same as the original message we sent. So it's actually like a ping. We send information to the device, get it back and check it. If it is correct, if the data that we receive back is the correct data, that means that both exchange to the device and the exchange back has worked. You might be thinking that this kind of test is very useful, and there might be an automatic function to do this. There is not. There is no automated feature in CUDA to do this automatically for you. You have to manually do it. So when you first start writing a CUDA code, one of the very first examples you will do is copy information to the device, copy it back but save it in a new place, and check the data. If you send an array, and inside that array is 1, 2, 3, 4, 5, 6, 7 up to eBay, and you copy the information back, and the Xin copy the data 都是0, your GPU has taken your money. You have to be a bit suspicious. So something is wrong. So we're going to use this test today to see if our copying is correct. So our test, we create a variable HA and define it. We're going to fill an array, HA. A is on the host, that's why it's HA. Fill it with 1, 2, 3, 4, 5, 6, some pattern, something we know. 2, 4, 6, 8 is fine, 1, 3, 5, 7, whatever. Something that we can trust. Don't use ling, 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 because that's just too convenient. If the GPU gives you something, it's probably going to be 0, 0, 0, 0. So something that you know, a secret password, I don't know, a pattern that you understand, saving A. We create another variable HB, it's empty. We leave that one empty. When we copy the answer back from the GPU, we're going to put it in B, and then compare B and A. If they're the same, excellent. If they're not, GPU is probably broken. Hopefully that won't happen today. We're going to create one variable on the GPU device, DA. After we set HA to a pattern we know that is not ling, 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 copy it to DA, sorry. Then we're going to copy it from DA to HB, and then check HB. Very, very good exercise. So if your HB is empty, bad. If your HA is empty, I don't know how you're going to test this. HB is not going to be rubbish. So let's give it a shot, shall we? Here is the code. Can you guys do me a favor and take a picture of this code right now with your phones? Now, 你应该知道我平常会放今天的那个 PPT 在那个 FTP 上还是网络上。I haven't put this there yet. If you want, I can probably copy the PowerPoint files to your directories in your Linux folders, but tonight I'll put this on the website, and that should be enough. 希望大家有办法拍照。如果你没有拍的话，希望你的隔壁的人有拍。If your phone is terrible, ask someone with a good phone to take a picture. So let's have a look at this code. First of all, this is obviously our C code. How do I know it's my C code? Because it has the int main folder. It has the int main function. Allocate memory, 这个就是跟你以前用的 allocate memory 完全一样。So you guys can modify the codes you wrote last week for this. Then we need to set A, HA. Don't just leave it 0. In this case, I'm using 0, 2, 4, 6, 8, 10. You guys can use any number you like, I don't care. And these are integers, but they're saved as floats. Send it to the device. When we send it to the device, we're going to send HA to DA. Get from the device, we're going to copy from DA to HB. Then when we print HB, it should be HA. If HB is 0, 0, 0, 0, 0, 0, then the memory copy has not worked. It either failed copying to the device or failed coming back. So this code is a code that I wrote for the Taiwan government to check, to make sure that the GPU devices that NVIDIA sold the government were working properly. So when you purchase 500 GPU cards from NVIDIA to install in a government supercomputing laboratory, I promise you 50 will be broken. When you plug them into your computer will say they're working, but they're lying. This is the only way to check. Copy information, grab the information back. If it can't do this, then that GPU is not going to help you perform a calculation because it can't copy data. So yes, actually this code revealed 50 broken GPUs and I needed to go back to NVIDIA and say, NVIDIA, you guys are criminals, please give us 50 new GPU devices. And they did actually in 3 days, which is not bad. Anyway, so this is what we're going to do. Please use your phones to take a picture of this beautiful slide. Here are your allocate memory and your send to device functions. This one, there's no magic. You can see we use HA and HB with malloc just like we normally do. Everyone's taking, no one wants to see me. Is that screen better or something? Aren't I beautiful enough? I used to be beautiful. Very good. Allocation of host variables A and B is identical to what we normally do. We only allocate DA because we only have one GPU array, DA, and we use CUDA-malloc for that. Sending to device, piece of cake, it's basically identical. It's identical to the code that I've written there. So everyone has this code now. Either way, using this print, we should be able to see what the errors are when we allocate memory and copy the data across. Last one, take a picture of this. This is basically identical to send to device, but it is get from device. The only thing that's changed is where the host is, the source, the destination, and the mode. 但是我要拜托你们帮我一下，我今天希望你可以帮我勾一些错 here or here. I really want to see if you can set the GPU on fire. It's in mechanical engineering, so if it does catch on fire, I need to run from here to that building as fast as I can. Should be very interesting to see. So you guys have got all the codes now. You'll notice that I've got my running shoes on today, so I'm ready. The code you're going to write today will be identical to the codes that you've written previously for GPU, for NVCC. You're going to have one C code, which holds int main. You're going to have one CUDA code, which holds allocate memory, send to device, get from device, and a single header file with the declarations inside for both. 所以其实其他的没有改很多了. You don't need to change your code much. You only need to take last week's GPU code, create 2 new functions for send to device, get from device, and you should be set. So, I'm hoping that you did not delete your codes from last week. Piece of advice, never delete any code. Anyway, 我们这里的考试都是 open book 考试，你可以用以前写过的 code 帮你加速。Well, I can promise you, 考试的时候我给你们的问题是跟以前你有看过的问题蛮不一样的。But it is good practice, and it will help you in the exam anyway. Right now, get it working. Do the test that I've just described to you. Create an array, copy the array to the device, get the information back and print its values so that you know it worked. I want you to write the codes down that you've just taken pictures of with your phone. 有成功的时候，请你给我看一下 and then we'll continue our class. Let's do it. Alrighty people, it's a long day, it's not over yet. We're just getting warmed up. I'm hoping that you guys all managed to write that code that worked on the GPU. If you haven't, that doesn't matter. We're going to come back to that. It is time to start doing serial computation on GPU. So, it is important that you did get that test code working today, because the test code that I've asked you to write, where we copy A to the device and copy that A back into D, B， 不好意思 B， 我们没有抛什么计算，我们就是 copy 而已。但是我们现在要做计算的工作。We're going to do some calculation now that it's on the device. 我知道听起来很夸张啊。It is not as bad as it sounds. It is very easy to write a code that runs on GPU in serial. 问题是 how to do it in parallel. So, this is for your information because you need to know that the GPU is like talking to a different machine. When we ask the GPU to do calculations, the GPU will perform the calculations that we want, but the CPU does not wait for those calculations to finish. Here is actually what happens. So the CPU, because the CPU is independent from the GPU and has a lot to do, so the CPU is going to say, hey Mr. GPU, it's going to give it an instruction. 那个 CPU 会跟 GPU 说, it's going to tell the GPU, you need to start running this function. So we write this in our code, and then when we execute our code, the GPU passes an instruction onto the GPU. The CPU passes an instruction. Then the GPU says, we send a command, and as soon as the GPU receives this command, 如果它有空的话, if it is free, it will start to perform this computation. But many instances, the work that we want to do on the GPU is a big work. If we have a small computation that finishes very fast, why are we putting it on the GPU? There's no reason. If this calculation is fast enough already, then why do we do it in parallel? There's no reason to. The work that we put on the GPU is going to be large. So the GPU receives this instruction, and we start computing on the GPU. Now, what is the CPU doing while this is computing? Well, let me ask you. When you're playing a computer game and the GPU is drawing, does the CPU wait for the GPU to finish drawing before it does its work? It can't. It doesn't. So when you play games, you have different FPS based on your GPU, but the speed of the game is still constant. CPU controls the speed of the game. The GPU is what dictates the FPS. We pass instructions to the GPU does our work, but the CPU does not stop. Control is returned to the CPU, and the CPU is doing nothing until that GPU computation is done. So while this is time, from here to here, the CPU, while the GPU is going, the GPU is working. And the CPU is going. It's doing nothing. It's waiting for the GPU to finish. Because these are two separate machines, the GPU has its own controller, its own schedulers. It is its own computer. We give it an instruction, it is doing its job. As soon as the instruction is sent to the GPU is free. So the CPU does not wait for the GPU to finish. Now this is important because when you guys finish this course, you guys are going to go back to your professors and you're going to take a code, and that code might take a week to run using one core. Then you're going to put it on the GPU, and you're going to start a clock here and have a clock here. And you're going to measure the time it takes to finish this calculation. It's going to say that the time between here and here is about 3 milliseconds. 所以你以前的一个礼拜的计算变成 3 milliseconds. So your speed up is like 500,000 or some massive number. What you just timed is not how long it takes to do the calculation on the GPU. What you timed is how long it took to send the command to the GPU and then come back. That's what you timed. So when we actually measure how much time these GPUs take to do their computation, we have a clock here and we start timing. We need to make sure the GPU is finished working before we stop our clock. Otherwise, it's very, very fast. And so every year I go to international conferences and someone tells me that their GPU compute time was 4 milliseconds. 3 to 4 milliseconds is a magic number. We know what that time is. It's a time to go there and come back. Every year. But I'm pretty patient. So, he's bored. What can we do here? Well, now, if we wanted to, what we can do if we have another GPU device. If we had another GPU device, then we can use CUDA to switch GPUs and then give the other GPU some work, which we can do. We don't need to use OpenMP threads, which are coming up in the second half of the course. We can just change GPUs and give another GPU more work if we wanted to. 如果你老师有请你看 multiple GPU 的计算, then you need to ask me about this because I'm not going to teach it. I'm not going to show you how to switch GPUs and then go. The computer you're using does have multiple GPU cards. Right now, all of you are using the same Tesla C2075. There is another very powerful GPU card in that computer that costs about the same. He is doing nothing right now because none of you guys have figured out how to switch devices yet. I'm not going to tell you how to switch devices. Everyone's going to love using that C2075. But 我就是要跟你说明一下，很多人他以为 control 回来的时候，那个计算已经结束了，这样是错的。GPU 可能还在想那个结果。So it's important that you know this. What we look for is for the GPU to send us a message when it's done. This is not easy to do. Actually, what we do is, this CPU is like a kid when you're driving to Kending. 我们到了没？还没。我们到了没？还没。我们到了没？还没。我们到了没？还没。这个是他的工作。我们要问他，你好了没？还没。你好了没？还没。你好了。到这里，你好了没？好了。结束了。That's how you do it. That's the only way. You need to check to see if the GPU is ready. So there is a special GPU function. I don't remember what the function's called because there's a better way to do it, but you can type this function and it will get the status of the GPU, if it's finished or if it's ready. So that's one way. Now, what does your first GPU function look like? That's it. If you had an ordinary function, an ordinary void function, it would look like this. But we're adding this magical thing on here. Now this is 2 underscores. Underscore, underscore. Global, underscore, underscore. I know that you guys are going to take pictures of this and then try to type the code. 2 underscores, 2 underscores. Global. What does global mean? Global is used by CUDA to say to the computer that this kernel will run on the GPU, but it is the CPU who told us to do it. 所以这个 function 是 GPU 跑的，但是是 CPU 给我们的工作。所以这个 instruction 就是 CPU 跟 GPU 说 ，Hey, Mr. GPU, 你要帮我跑这个 function. So global means that everyone can use it, including the CPU, 因为有另外一个 function, 另外一种 functions 可以跑在 GPU 上 but only the GPU can launch those functions. Those are called device functions. And we will come back to that in 2 or 3 weeks. But for now, global functions launched by the CPU but run on the GPU. So here we have a function. I love this function. What does this function do? Nothing. It does nothing. It is the safest function you can run on the GPU. Void. Every function you run on the GPU is going to be void, except device functions. So if you see global, 后面会有 void. Because what does that function mean? Normally, if we said float GPU function, that function will produce a float and give it to us, right? Can the GPU give you anything? No. GPU can't give you anything. If you want to get something from the GPU, you need to use CUDA memcopy to get that back. GPU functions cannot give you anything except device functions. 所以 global 后面一定会有 void. 如果这里有 void 的话，这里可以有 return 吗？ No. So there's no return. So this function will compile and it will run. And it does nothing. We do include access to an array here. That's pretty convenient. 这个 A 就是一个 array. 对我们的话应该是 DA 吧。Can we put HA here? Please try. today, I want you to do it. I want you to try to create a GPU function that uses HA to do a calculation. I want you to see what happens. Nothing is going to happen, I can tell you that. It's going to crash, but it won't give you an answer. So a kernel looks just like a normal C code, and it is almost like a normal C code. But this is CUDA, remember? It's like C, but it's not C. But there are some differences. When the CPU calls this function, the CPU is going to tell the GPU, hey, GPU 先生，帮我跑一下这个 function. 但是那个 GPU 上有好几千个 cores. The GPU has thousands of cores. So the GPU is going to be like, okay, how many cores will I use? And which cores? We need to tell the GPU this information soon. Of course, this underscore underscore global underscore underscore 一般的 C 加 GCC compiler 应该是看不懂吧? The normal compiler does not understand this. This is CUDA. 所以这个 function 一定要放在你的 CU file. You must put this function in your CU file. We can use the CPU to call this function, but you're going to see how that works soon. We need to be able to find a way to modify this to be run by the CPU. We're going to use a wrapper function for that. So a wrapper function, you guys have already all written wrapper functions. A wrapper function is where we write a function to execute functions that a normal compiler does not understand or cannot perform. You have all written codes called allocate memory. Inside allocate memory, we use malloc and CUDA malloc, right? And that code is put into the CU file, into your CUDA file. And we use our CPP file inside intermain to call allocate memory. So that function is a way that we can take instructions for the GPU and execute them by the CPU. So allocate memory is an example of a wrapper function or a wrapping function. The function that we use to launch our kernel is going to be the same. Let me write this down so you guys can see. Underscore, underscore, global, underscore, underscore, void. I need to pick a function name. Why have I written this here? 希望，我是希望这样是够明显的 underscore underscore global underscore underscore void 一定是 void. Cats are cool because they are. We write our function here. We close our function here. We do not return anything. 不可以用 return. Let's see how this pans out, shall we? But how do we call this? When we call this, we need to tell the GPU some information about how many threads to use. So we need to create a special function which is going to be used to call our GPU function. So here is our GPU function. Underscore, underscore, global, underscore, underscore. I love repetition. That's our GPU function. He doesn't do anything. But we need to find a special way to call this. Here it is. Here's where we call our function. GPU function, here's his name. We pass DA. Try passing HA later. But this is a GPU function, so this must be GPU variable. What the hell is this? Information about how many cores to use, basically. In this case, we have 1, 1. I don't want to go into too much information about that, what that 1, 1 means now, because normally when I teach students what that 1, 1 means, people's heads explode and blood is on the floor. And if they don't die, they're crying over there, or they just jump out the window. The total number of threads or the number of cores to use on the CPU here is the first number times the second number. So if we launch our function, that's a big C, cool, smaller than, smaller than, smaller than, 1, 1. This is AB. 1 times 1 is 1. So we're telling the CPU, the GPU, hey GPU, please execute this with one core. One streaming processor. Actually, we can't control the streaming processors on the GPU, but we can control how many threads to pass to how many streaming multiprocessors. So this is one streaming multiprocessor, one SMP. Remember, every SMP has 100 cores inside. This is one thread per SMP. So one SMP with one thread, that's one thread, one total thread. So if you feel like throwing yourself out the window or you start crying, just chill. I can explain this. Next week we actually do go into parallel computing. The week after next week, actually, because next week is theory. But serial computation, and cats are cool takes one variable, dA. That's how we call it. And we place this because if we put this smaller than, smaller than, smaller than, larger than, larger than, larger than, 如果我们放这个进去一个 C code, if we put this into 一般的 C code, the GNU compiler is going to be very upset. GCC, G++, they don't know what these are, but CUDA does, NVCC does, so this function must be put in the CU file. But inside int main, we call this one. So here's our int main, this is CPU code. We're going to call launch GPU function, and we go over here. Then we call this function with one thread. That's all you need to know. This is a serial calculation. And then we're going to run this code on GPU, but he's empty for now. Take a picture. But we have a better code coming up, but you should definitely grab a picture of this. All right. So now we're actually going, hang on, there you go, take a picture. Just in case someone missed it. Is everyone ready? Very good. Let's actually do some work, shall we? In this instance here, we have a serial code. So this is a C code. How do we know this is a C code? There's no global stuff here. So this is just an ordinary C code. Inside this C code, we're going to take array A here, and we're going to double A. See how we're doing this? We double every element. So each in, if our array A is 1, 2, 3, 4, 5, 我们的新的 A 就是变成 2, 4, 6, 8, 10. We can double it. So for I equals 0 over all n's, n is global or defined here. I++. 新的 I 就是旧的 I times 2. This is a serial job. If we have n elements, then this thread must do all n elements. So we have one core, and the core must do all of these parts, the whole array. If we have two cores, 这个工作应该可以分享吧? We can share the work. If we had two cores, we could say, oh, core number 1 do half of n. Core number 2 do the second half of n. And 我们可以这样分享. In the GPU later, we will share the work. But today, we will use one streaming processor, streaming multiprocessor, with one thread to do the whole loop. So let's take this serial function, the CPU code, and change it to a GPU code. How do we change this to a GPU code? 我们要做什么? We just need to add global at the front, and that's it. In this case, we don't have to do anything at all. Yeah, already done this. There we are. Done. There's my CPU code. There's the GPU code. If your teacher has asked you to take his CPU code and change it to a GPU code, there's the answer. You just put global in the front and you're finished. But this is not going to run in parallel on the GPU. This will use one streaming processor. It is going to be extremely slow, much slower than one CPU core. Because a CPU core, the i5 or i7, the CPUs and the server you're using are Xeon Xeon cores. They are fantastic. They are very powerful cores. This is going to run on one thread, one tiny little core inside that GPU card, and that CPU inside the GPU, 它以前习惯做这个工作，画图. He likes to do pictures. And in this case, it's, you're not doing pictures, you're doing computation. 他没有习惯这种工作, so he will be slow. So to make this run like this, we just need to add global and we're finished. Of course, we're not done yet. We need to make a wrapper function for this. Yeah. We only needed to insert the global stuff. Nothing else makes any changes. 你要记得我们用一个 thread 在 GPU 上，那个 thread 也是要处理所有的 n 个 elements. So all of the threads on the one thread on the GPU will take care of all n elements. If n is eBy, and we have 100 threads on the GPU, we can share the work easily. We can ask every thread to do one part of A, which we will do in 2 weeks' time. But today, 今天一个 thread 在 GPU 上，所以那个 thread 要做所有的工作，所以其实那个 code 是一样，没有改变，因为两个都是 serial. We are almost ready. Yeah, add the global, and then you're finished. This A here, global, float A, do whatever you want. Use the host A. Have fun. It should be the device A. That A must be on the GPU. If it is not on the GPU, something's going to happen. Please show me what happens. I can't wait to find out. Bad things will happen. So here is our code that we might use. You're going to see that it's basically identical to the code that you just wrote. Allocate memory, set A. Last time we sent to device and then got from the device and printed out HB, right? But this time, we're going to slot this extra core GPU function in there. So 现在我们的工作是一点不一样. The work has changed. Before we copied the information to the device, copied it back and checked to see if it was the same. Now, 应该是 double. When we check HB, it should be double HA. So this way we can check to make sure the copying worked and the calculation worked. So, I hope that you all have your working GPU codes. If you don't, that's okay, I'm going to help. Then you need to modify your codes, probably save a copy of some new codes. Modify the new codes to add this function. Where are your other functions? There, you shouldn't need to worry too much about these. These are allocate memory, free memory. Send to device, get to device. Go, there you go. Take a picture of this. There is your GPU serial function. Sorry, here is your GPU function, and there is your CPU wrapping function. So when we call our serial function, we'll call that function. So 其实你只要改你的 code, include these functions而已. So because your code has called GPU serial function and this global void GPU serial function, these functions need to be declared before they're used in your code. You have two options for this. This call GPU serial function you can declare in your header file. That's okay. You cannot declare this sucker in your header file because it has global in front. Your GCC compiler will not understand that. So you need to declare this function in your CU file at the top, or define this function before you use it. That is the other option available too. If you put this code at the very top and then write this code underneath, because this code here needs to be placed in the CU file, just like this one. 如果你先放它在上面 compiler 到这里的时候，它已经有看完了这个 code， 不用再 declare, because it understands. Has everyone got their pictures? Excellent. We've got this, you just took a picture of that. I think we're set. Here's the makefile. If we originally had 0, 2, 4, 6, 8, it's going to be 0, 4, 8, 12, 16. depending on how you allocated your thing. You can see when I showed you my main file, here we are, see. When I set my A was originally 0, 2, 4, 6, 8. 所以那个结果一定是 0, 4, 8, 16, 32. So you can see, when I run this thing, when you get this answer back, 0, 8, 0, 4, 8, 12, 16, 成功了, it worked. I know it did, because these numbers are right. If this is 0, 0, 0, 0, 0, that means that the calculation function did not work or the memory copy did not work. 你应该有两个工作，应该是先 check 一下你的 copy 有成功了. If your copy code worked and your B is equal to A, insert the calculation function and then try doubling A to see if it worked. Okay. Do it. After you've done this, after you've got this code working and HB is double HA, make this code run on GPU, please. That will be the really interesting part. So you need to take the code which I asked you to write at the beginning of today's class and make it run on the GPU. Good luck with that one. I'll be in the classroom until you guys finish. Please keep in mind that we want to go home before 7 p.m. Good luck.